Welcome to a new test and teardown video. This time it's a general microwave model 454A thermoelectric power meter, and it's tube based. We got 3 different major ranges: 1, 10, 100 watts. So that is the highest input it can accept. And we got a 0 here, I guess. And then that will be the full scale ranges. You dial this one. This one is completely stuck. So of course I have to open and do a careful inspect. I also got the probe. And this probe here, you've probably already figured this out since it says thermoelectric. That means inside this probe we got 2 temperature sensors. One temperature sensor is directly connected to the input, of course via a little bit of matching and all that kind of stuff. But that temperature sensor is heated up by the RF input power. All right, and then there's another reference temperature sensor of exactly the same type, and it's measuring the ambient temperature. So the idea is this system here measures actually the temperature rise on the sensor that is connected to the input and compare it with the ambient temperature. That means that will be your input power, the power that is needed to warm up this one, right? So you can imagine full range 0.3 microwatts. That is the power needed to warm it up to full range. I don't know if you're a little bit impressed, but I am. So frequency, because this is this temperature system, these kind of things measures really high frequencies. So we got a little calibration dot here to 12 gigahertz, but obviously it goes to 14. And when this was new, we had some more dots. So 10 gigahertz, we got 0 deviation, and that is it. Okay, this is the percent or something like that. There's another dot right there. What does that say? 100%. I think efficiency or something like that. So the idea is, if you know in what range you are, you simply just change this little dial here on the back. See? And then it is compensated again. So it was it? If I know I'm gonna play around with 12 gigahertz, see, I'm right here. Okay, so this is 9.3. So I put this for 9.3 like that. And then my measurements will be accurate. How about that? So how old is this thing? Yeah, I got the manual. I got the full manual with this one. And that tells me this one was installed at this local military airfield, and they even wrote the year 1966, and then probably later it was sold to this guy. And so that is the story so far. And yes, it's from New York and all that, so it has already been a little bit around. And this manual is really that old. We'll have all the different specifications. Yeah, see exactly what I just said. Full range for your 0.3 microwatts. Frequency range, yeah, everything here. And of course a nice picture and all that. Here we got the weight and the size and all that. There's one more really cool thing I want to show from the manual before we start the video. Here is the block diagram of this unit, and I think it is, of course, there's no big surprise. There's a chopper. So here's the input, and there's a chopper. It selects either the measured signal or the feedback system. All right, and then we have all the different gain system here in the feedback, and then you compare how much you set up all your feedback, and then you can of course measure the difference. Then you know exactly how much signal you got. And as far as I understand, all this is tube based. We'll look at the schematic in a second. Zero control, of course. I should maybe scan this or see if it's already online. But of course, the power supply consists of everything here. Of course, this is from 1966, or this is the purchase date. So maybe the design here is a little bit older than that. But as you can see, it consists of both transistors and tubes. And here in the power supply, we also see a normal rectifier bridge, high voltage rectifier, and then a tube-based high voltage, regulated high voltage supply. That is pretty cool. And then this here is important. So this is the low voltage AC. It's driving this coil. So this coil is a part of a relay, mechanical relay. And I don't know if you can understand the timing requirements for a mechanical relay that is just swinging constantly on mains frequency. Here is 1/2 of that relay, and this is of course the connector for our sensor. And you can see the input goes either to the measured signal or phase or out of phase and all that kind of stuff, and then it goes to the amplifier, first tube amplifier. And of course, each of the amplifiers, they are only running on AC, and that means the amplified signals goes through a feedback, AC feedback, and that means any properties of the tube is completely irrelevant here. It's only the feedback system that makes the controlled gain we got in this one. And this again, local feedback variable with the settings, and then you have your input and then your feedback. This is how you do it to make it nice and accurate and stable. And then again, some more gain. Of course, you need all this AC gain because you can measure insanely small input. I mean, really low input. And here is the other part of that relay. The switches in phase with the input here, right? Measured reference. And then some transistors. Now the signal is pretty high, and then it goes to the output. Yeah, that is the schematic of this thing. Yeah, of course, I see some corotion and all that. I don't know exactly what that is. On this one we need to correct a little bit. Here's the high voltage power supply, and as we can see here, one of these, this one is starting to get white on the top. That means we should expect low emission on that tube. And this is something I need to verify. We got some leaked capacitors right there and there. See, the acids left this around those capacitors, so this is not so good. And here we got low thermal cadmium solder, and there's a reason for that, because any joint of different materials generate a voltage difference at temperature, right? So this is how many thermal measurement systems actually works. Take advantage of this. But what we don't want here is to add another temperature dependent readout, because we are actually measuring temperature when it comes to the bottom of it, right? And that is why we got this little label right here, and it says we need to re-solder red marked joints only with this solder, right? Use only a clean, yeah. Bare copper tipped. Interesting. I want to look in there. And this is the switch that is not moving. Something is maybe broken in here. Look at this circuit board design with hand-written numbers and stuff like that. Huh, pretty fascinating. So I believe in here is the connector for our input, and that will be the double relay system. The drive signal is here and at the top, I bet. You'll see. And it's of course inside a little vacuum. Absolutely high end. That is the first amplifier tube, and it's mechanically vibration isolated, decoupled, because this little vibrator of course moves, and you don't want any of those vibrations or harmonics of the vibrations to go into this tube and be amplified and cause problems. Aren't you a little bit impressed? And that will be the next two stages. And again, here is a tube that is losing vacuum. It's normally supposed to look like this. Got some funny dirt around this, and then the little transistors and all that. Beautiful design. So here's the little input shield room, and that will be the red marked solder points of super high importance. This is of course to avoid creating any voltage differences versus temperature, of course. The blue part here is, it's actually set here R56. It's a 10 ohm resistor, and this we see here, that is the bottom part of the relay. It says here G1A, and the part down here under that switch is the first transformer. I was able to get this switch moving. Still need, a good solid hand, but we can. Yeah, okay, it's getting slowly better. In the manual, it says about the different power heads. The N422 is the power head I got. And here is the frequency range in gigahertz, and maximum power is only 1 milliwatt. So that is important to remember. And of course, if you don't know that, you could accidentally select 100 milliwatt. This is of course a full range and all that kind of stuff. And with the 1 milliwatt, the needle's just gonna lift a little bit, so it's much better to go like that. Now we have 1 milliwatt watts full range, and then we can see what is going on. I think I will try and power this up and see what is going on with the power supply, the voltages first, and see if that is any good. It says, of course, again in the manual how many volts and how much ripple and all that kind of stuff. So it should be quite easy to try and power it up. I did clean it up a little bit, so it is now nice and shiny, sort of. We can still see some water drops or some stuff that came in here, and it probably also affected the rest of the board, but let's try and power it up and measure the voltages and see if there's any life. So I feel I am ready to try the first power on. I put the sensor on, and I am now in the 1 milliwatt range. Everything is up here, and this here should be the 0. And let's just try and connect power here. This is my 200 volt regulated anode supply. And look at that. This sound you hear is this relay. This is completely normal. And you can see the 0 is actually affected a little bit. How cool. I really want to try and put on a signal. This one should go to 100. Yeah, let's go and get a signal generator. So here we go again. All I did, I picked up a little signal generator, and let's just try 1 gigahertz for starters, and 1 milliwatt is my output power. And when I click this button here, we will have 1 milliwatt, and it should go all the way to 0 dB if everything works. Are you ready? Nay, but it actually did lift a little bit. No, that was bad, huh? So I expect we don't have all the gain we need. Let's try and see if we can go down some ranges. Then we can 0. Yes, we can. And let's try and... Aha, and here we go. So this tells me we need much more gain. Like a gazillion. Let's try and 0 this one. And then minus some dBs and all that. I really want to sit and play at the moment. It's so much fun to see if it really works or not. So here's what I've done. We are now in the minus 20 dBm range. I just zeroed the readout to 0 dBm. Maybe we should go a little bit closer so we can see what's going on here. Like that. So if I dial the input power down to -1, it goes to -1 more or less. -2. Nah. -3, -4. So definitely something is working. Maybe the input attenuator here is broken. I really don't know exactly what is broken. I found in my manuals and all my documentation information about this unit being broken, and about there's a funny note saying here, so somebody here wants to repair the unit, and I can translate this a little bit about very good luck with calibration, all that kind of stuff. So it's a lot of fun to find stuff like that. So this one was definitely sent for repair, and they gave up on it anyway. So I don't have the equipment to calibrate this. I mean, this unit here should be accurate and all that kind of stuff. Well, of course, I'm gonna go and play on with different tubes and see if I can get some more gain and all that kind of stuff. But I just wanted to show how this works and what is the main features and the general things and all that. Oh, there was one more little detail about all this schematic stuff, and that is I found a manual online on eBay. You can buy this manual for only $13. Well, what I've done, I scanned my entire manual, and it will go online on peel.dk. I will put a link in the description for absolutely free, where you can download this manual. And also I got all the manuals about the power heads and the instruction manuals for power heads, and yeah, all the material that I found is of course online for free, as it should be. So since this sensor head seems to be not giving the right output, I want to open and have a look. It says here 100 milliwatt average output power, so it can handle more. Well, that is a little bit interesting. The manual says differently. But I think all we have to do is just take those screws, and then it's probably gonna pop open. Let's try and have a look. Okay, see what I figured out. I also got the manual of the power head that explains exactly. It doesn't explain exactly how to open it, but there is a nice little exploded view. And the thing is, it says here the first thing you need to do is to verify the resistance between 1 and 3, and this should be 200 ohms, and that is not the case. This is pin 1 and 3, it says, of course. That is not the case. So that is, of course, why it's not working. This one is blown up, and I'm trying to figure out how to open this, because if I look at this funky exploded view, it doesn't really say how to do the magic. You see, here's the elements, and we got some all sorts of parts and whatnot. But the thing is, I removed all those screws, and I'll remove this so I can pull this out here, and I can hear that it's doing some things, and there is a little secret mark right there. So somebody used a screwdriver to try and crank this open. Maybe that is how it's supposed to be done, because I really don't want to. It's, of course, now it's too late because it is completely blown up, and I'm not going to send this for replacement anyway. Maybe one day I can find one that is working in a, or something like that. I don't know. It's probably never going to happen. So let's try and open it anyway. That's exactly what I did. Remove the dial. Remove the throughs. I got hurt, yeah. Washers, la la la. You see, strip the housing. Sounds easy, huh? But none of this works. There's no way to slide anything. Damn it. Just a little more violence and we're in. So, what can we learn from this? So far, we can see there's a little thermistor in here, and this is for the reference of everything here. And if we get into that unit, and I think we need to remove a little bit more before we can get in there. How can I get this off? Okay, so those two wires here, or two connections here, we got some little spring-loaded connection system and some copper wire that is not soldered but pressed in somehow. And that is, of course, the connection to the sensing thermal element. And here's the other one measuring the temperature of this casing. But what I realize is this. See, it's completely loose. This one should, of course, not be loose. And if I do like this, dibbity dibbity dabbity, I mean, it should be good connected to that one, right? And I think you release these by pressing here and then, yeah, exactly. See, press and pull. This is how it works. Ooh, this feels weird. We want to go in here and have a look. Ah, that will be the standoffs for the circuit board. That is beautiful. I did not expect it to be this pretty. So it connects to these 2 points. I can take my ohm meter and verify if we got the 200 ohms we need right here. Oh, we see the corrosion here. From the right angle, it looks completely corroded around this point. Also around this one. That is totally jammed. Yeah, 300, damn it. So that is why it's not working. I think it's really fascinating that 12 gigahertz goes through here, and that just, this is the 2 resistors that connects to this, and then it measures somehow. Can we? Oh, yes, we can. Oh, there's a tiny little screw here. Hang on. That is one tiny little screw. I don't know. I don't have a banana for scale, but oh, this is tiny. Oi, don't get lost. And then we should probably be able to lift this element, because I read in the manual the resistor element here is actually field replaceable. In case you blow this up, you can replace it. I really want to get it out without damaging it too much, because I really want to see the backside is where the real... Oh, come on, man. No. Oh, we can see some shoot-throughs here. And we can see all the corrosion, and I don't know if that is visible. But see? This is how it looks when it's blown up. We can even see through it. That is what happened. Oh, so this is the few little milliwatts of resistor thermal element. But isn't there? There should be an attenuator in here, right? Where's the 50 ohm load for the input? I mean, that should be in here somewhere, right? There's no way I can get further into this thing. This is just one piece of magic. Oh, damn it. I did not expect that. There's no DC connection from the center pin to this part at all. And there's no connection from this one to chassis either. So, I mean, is there just a capacitor or something in here? But where's the 50 ohms? There's no 50 ohms here. Because this one measures, of course this is blown up, so maybe that is why. But I feel we got more to this than just what we see, because there must be an RF signal, and this is a capacitor, and then you have the 50 ohms, and then on top of this element, yes, here we go, see? We got more layers, and then there's a resistor and a thermistor on top of each other here. So that is the magic behind this thing. Well,